So when we look at our FRW metric, we actually see a value in here of k. We've derived it for a positively curved three-dimensional space. But in practice, you can have any curvature potentially like, and in fact, there are really three possibilities that you can look at for the geometry of the universe. So you can start with k equals 1. Sense of where we started this derivation from. The universe is positively curved. So think about it. What does that mean? Well, a positively curved 2D space like we're used to living in, if you keep going in the same direction, you come back to the same point. And the same is true in the universe. So a straight line, i.e. a photon, on a null geodesic, will eventually come back to the same place. You can have k equals 0. This corresponds to fat space. The universe is flat, x, y, z orthogonal, etc. Note, this is flat space, it is not flat space-time. And then k equals minus 1. That is a negatively curved universe. You'll sometimes also see it's called a hyperbolic universe. And in that case, straight lines diverge. And so here I have a curvature, which is a fundamental property of the space. So it's not like a Newtonian fudge where I say it's, it's the energy must cause curvature, which doesn't happen at all in the Newtonian case anyway. I've actually derived a metric which allows me to have a curved space-time. And without going into any detail, I'll say that observations of the cosmic microwave background and that's 400,000 years post-Big Bang recombination. So basically, it's when the universe becomes neutral, atoms form for the first time, so the electrons are captured by the protons and become hydrogen. The process is called recombination, which is very badly named because, in fact, the universe was never combined before that. At that point, you get this sort of signature of what the universe looked like at that moment it recombined. That gives you a route to measuring the curvature, and there is no curvature. It's flat to about 0.1%, based on new things like the emission from the European Space Agency called Planck. If you're interested, please do go and look that up, but I'm not going to go into that because in a sense that's a more astrophysics problem than a general relativity problem. And I'll just finally note that there is an alternative way to write the metric, and you'll see this quite frequently in some textbooks, so I'll put it in, which is to write ds squared equals c squared dt squared minus a of t squared d chi squared plus sk of chi squared d omega squared. And here sk takes different values. for different k's. So for example, sk is equal to sine k for k equals 1. It's equal to k for k equals 0. And it's equal to sine k for k equals minus 1. It doesn't change anything of the physics, but it's just an alternative way of writing it down. And some things become a bit clearer when you work in that notation. But it's really just for completeness that I'm putting it in here.